Okay, so this is a synopsis of what you need to know for periodic trends. This is not a full-blown class lecture because my recording didn't work yesterday, so I'm just running through and touching on the highlights for trends. For more information, you need to see the in-class notes, online notes, or your textbook. So we started out yesterday talking about trends and their importance, and to understand trends you have to know your definition of both your valence and core electrons. Valence electrons being all the electrons on the outermost shell, and any other electron is going to be a core electron. We talked about the importance of effective nuclear charge. You do not need to necessarily know how to calculate it, but I will go through calculations on the next slide to show you how it may be applied. All that's important is you know that effective nuclear charge is basically synonymous with nuclear pull. So moving on, we started out discussing the trend of atomic radius. As you go down the periodic table, atomic radius increases due to something that the AP people like you to term as shielding. Again, this is a quick synopsis. I discussed more about shielding actually in class. Please see notes for that detail. As you go down the periodic table, you're increasing your number of energy levels. So your atom is going to get bigger. As you go across the periodic table, radius gets smaller. Why is that? That's the case because not only are we adding protons, we're adding protons to the same energy level, which increases the nuclear pull. So increased nuclear pull as you go from left to right across the table. You can also use as an argument increased Z effective or increased nuclear charge. Those are all synonymous. Nuclear charge, because again, we're adding more protons to the same energy level. An example of the use of Z effective calculations to prove a point, the formula from the equation from the previous slide said to find Z effective, you take the atomic number, so for nitrogen that would be 7, minus the number of core electrons would be 2, so our Z effective is 5. Versus fluorine has an atomic number of 9, number of core electrons is 2, for a Z effective of 7. The larger the Z effective, the stronger the nuclear pull, therefore the smaller the atom. Again, you do not need to calculate this if you don't want to. That's just for those of you who like numbers and like equations. That would be a way to prove an atom is smaller than another when you're within the same period. Do not use Z effective or nuclear when you are going down the table, down a family. You only use it for across the table, because as you go down the table, Z effective does not change. All the alkali metals have the same calculated Z effective, so you can't use that as an argument. Then the same thing with shielding. Do not use shielding going left to right. You can only use it when you're talking about a column up and down. So be sure to keep those straight. Next is ionic radius. When we're dealing with ionic radius, it's very important for you to know the term isoelectronic. Isoelectronic means same number of electrons. So there's going to be 3 different scenarios that you need to take a look at when we're dealing with ions and their sizes. So for example, if we were to compare Mg plus 2 to Sr plus 2 to Be plus 2, the first thing I really want you to do is decide what noble gas these are isoelectronic with. When magnesium loses those 2 electrons, it's isoelectronic with neon. This is with krypton, and that is with helium. So to rank their sizes, you can now just base the size on those noble gases. And we know that helium is smaller than neon, which is smaller than krypton, which is great because now we go back and translate that to being Be plus 2 is smaller than Mg plus 2, which is smaller than Sr plus 2. And there we have our ranking. Again, I want you to look at what noble gas these things are isoelectronic to for comparison, because I could end up doing something like this, or the AP could end up doing something like this, where they give you things that are scattered all over the place. They might say compare S minus 2 to Ra plus 2 to I minus. That's a little daunting, and students are like, oh my god, what do I do? Well, what you do is find what noble gas these are isoelectronic to. So when S gains, it's 2 electrons, it's the same number of electrons as argon. That's isoelectronic with radon. And this is isoelectronic with xenon. So now we're going to rank these, and we end up getting, we know argon is smaller than xenon, which is smaller than radon. So that means S minus 2 smaller than I minus 1, smaller than Ra plus 2. This was a lot more daunting when we didn't have the noble gases as a comparison. The third scenario is a case where we have, this is tricky, and this is what you're going to see most often actually, Cl minus being compared to something like Ca plus 2 being compared to P minus 3. So here again I want you to find what noble gas these are isoelectronic to. That's isoelectronic to Ar. Uh-oh, they're all isoelectronic to Ar. So what do? What we're going to do is base it on charge. Based on charge. So what do I mean? Based on charge means I'm going to look at the number of protons. We know these all are isoelectronic to each other, so they all have the same number of electrons. The one with the most protons, meaning the largest positive charge, is the one that's going to be the smallest because the nucleus is pulling harder on that same number of electrons. So we rank it from the most positive being the smallest to the most negative being the largest. And again, you can only do charge comparison when they're isoelectronic to each other. Here, we don't do a charge comparison. Students will want to now knowing this whole trick, they're like, oh, I want to put plus 2 first because plus 2 has got a positive charge. Well, you can't because these all are different sizes and have different numbers of electrons, unlike these that are isoelectronic to each other. All right, moving on to our next trend, ionization energy. Ionization energy, by definition, is the energy required to remove the most loosely held electron. So an equation that's an example of this would be, if we looked at fluorine, fluorine positive plus 1 electron. The energy required to make that reaction happen would be considered the ionization energy. So the general trend as you go across the periodic table, ionization energy increases, because of increased nuclear pull. It gets harder and harder to remove an electron the smaller the atom is. That nucleus is holding on for dear life. It's not going to let it go if it's super tiny. As you go down the periodic table, ionization energy will decrease because of increased shielding, therefore less nuclear pull. The further away that nucleus is from its valence electrons, the easier it is to remove those electrons. And let's talk about some exceptions that I went over in class. They occur in 2 different spots. I'm going to do the exception between the N and O families first, and then I'll talk about the exceptions between the B and the Be, the beryllium and boron families. The exception between nitrogen and oxygen is a little bit easier to explain, so I'm starting with that. According to the trend, if we look at oxygen's valence electrons, we have 2 s's and 4 p's. Nitrogen, on the other hand, has 2 s's and 3 p's in its valence shell. So if we're looking at first ionization energy, we're comparing that electron to that electron. Based on the trend going from the left to the right, it should be more difficult to remove that last electron. Should be more difficult, but not. We have to explain why. Well, the reason has to do with the existence of repelling forces in that particular orbital. Do not use the argument that this electron is half filled. That orbital that electron is in is half filled, so it's more stable. The AP exam does not accept the argument of half filled orbitals being more stable. That's a correct argument, but it's not a reason. Why is a half filled orbital more stable? Because there are no repelling forces, no repulsive forces. 2 electrons in one little bitty space, not a happy situation. So existence of repulsive forces makes it easier to remove that electron. Okay. The other exception is in our beryllium and boron families. Beryllium's valence electrons are strictly 2 s's, and boron, we've got our 2 s's and a p. According to the trend, it should be harder to remove that electron because it's further to the right, but it's not harder. Students are really perplexed by this one because they're like, hey, it's alone. While this electron we're comparing it to is not alone. Doesn't that have repelling forces? Well, what supersedes that is based on the shape and the proximity of the p orbital to the nucleus. If we compare the s orbital, this is the s orbital, to the p orbital, you can see that the lobes of the p often extend out beyond the s orbital. So there are going to be moments in time where the p electron here, this p electron, is further out from the nucleus than the s electron. And so an average, if you kind of average out all the energies, it is going to be easier to remove that p electron. Easier to remove. So easier to remove p electron due to shape of orbital and proximity to the nucleus. So those are our 2 exceptions. If I were ultimately to graph ionization energy versus atomic number, I would see 2 dips, and then I would see level 2, 2 dips, and so on. So what those dips are, this first one is your N and O, and the second one is your B and BE family. And again, these trends follow all the way down the families for all the pairings there. You get that same weird thing happening, that same exception on every single period. Our next trend, and actually it's not another trend. I'm going to insert another blank page here. This is continued discussion of ionization energies. If we look at something like magnesium's first 3 ionization energies, meaning I take away 1 electron from magnesium, another electron, and another electron, you'll see a pattern. I'm making these numbers up, so please don't quote me. Let's say it takes 500 kilojoules to remove the first electron from magnesium. Let's say it takes 5,000 to 15,000 kilojoules to remove the second electron. Well, that makes sense. It's harder to remove an electron every time you take one away. It gets more difficult because of the positively charged nucleus. More electrons you remove, the more proton to electron ratio you have, the harder it is to remove. But when we get into a scenario here, if we were to remove magnesium's third electron, we'd see some crazy big jump in energy. So a lot of times the question you'll see is, why is the third ionization energy of a magnesium atom so much higher than the second? And your argument would be, and you can look at your periodic table and see this, your argument would be that you're removing a core electron at this point. And this totally makes sense because you never see Mg plus 3. You see Mg plus 2, right? Okay, Mg will not be plus 3 because of all the extra energy required to move that core electron. Do not, under any circumstance, say, oh, it's stable because it's like a noble gas, or it's happy. You will get 0 points for that type of personification. And it's not really a reason. Being happy is not a reason on the AP. Okay, electronegativity. We're not going to deal with much with this. This is pretty simple. Electronegativity is basically the attraction of an electron to an atom that's bonded. Attraction of an electron to an atom in a bond. Okay, so the most electronegative element is fluorine. We call our fluorine the floozy. Fluorine is the most electronegative. Why? Because it's the smallest atom. It's got the strongest nuclear pull. And the reason we don't say something like neon, which is smaller, remember, neon doesn't react due to its full outer shell. So because it doesn't react, it doesn't form a bond. Therefore, it's listed as having a 0 electronegativity. So fluorine is your most electronegative element. Francium is your least electronegative element. So the further away you get from, the closer you get to fluorine, the more electronegative. The closer you get to francium, the least electronegative. So as you go across the periodic table, electronegativity increases. As you go down the periodic table, electronegativity decreases. Okay? That's all I need to say about that one. It's a pretty simple one. Moving on to one that's not often covered, and I don't want you to freak out about it, but I do want you to think about delta H and signs of delta H. How electron affinity here differs from electronegativity is here we're looking at the attraction an atom has to an electron just sitting off by itself, basically in space. Okay. This could be represented with the equation. Say we had element X, we add an electron to it, we get X minus. The energy that either takes or gives off is the electron affinity. So electron affinity can be positive in some cases and negative in others, and that's what I want to talk to you about. Let's start with the idea of francium. If we were to add francium to an electron, it would not be a happy day. Francium is a metal. Metals do not want to be negative, and francium being so large, having such a low electronegativity, having such little nuclear pull, does not want an electron. It's doing everything to get rid of its electron. It's so incredibly reactive, it's throwing its electron. So why would it want to take an electron? It doesn't. So to make that happen, I have to put energy in. That's endothermic, putting energy in. So francium's electron affinity is a very big positive number. If you look at something like fluorine, fluorine's a different story. Fluorine's like, heck yeah, I want that electron. Fluorine, as you know, is super electronegative, super small. It's basically one electron away from a full octet. It is really excited. It's so excited about having the electron that it's given energy off when it gets it. It is exothermic. The process is exothermic, therefore its electron affinity is negative. So, to sum it up, as you go across the periodic table, electron affinity becomes more negative, that's towards fluorine. And as you go down the periodic table, electron affinity becomes more positive. Okay, so I will just work one really quick problem here for those of you who were absent. The rest of you only need to come in, copy from the online notes, and ask questions. But number 18, it says the atomic radius of magnesium is smaller than barium. I know you guys want to write a book. I know you like lots of words. But if you simply say barium having more energy levels or shielding is larger. That's it. All you have to say, more shielding, more energy levels. That's why it's larger. The next one, the ionization energy of S is lower than P. I'm going to be pretty insistent on these types of problems. Instead of trying to sit there and in words describe what's going on, draw out your valence shell orbital spin diagrams. Okay, so we know that sulfur has this, and we know that phosphorus looks like this. And according to the trend, this one is supposed to be harder to remove, but it's actually easier. Hopefully you recognize this as being one of the exceptions for ionization energy because it's directly below the nitrogen-oxygen family. Well, it's in the nitrogen-oxygen family. So this electron should be harder to remove since it's to the right of phosphorus, but it's easier. And the reason for that is due to repulsive forces in that first p orbital. Again, do not say half-filled orbitals are more stable. Okay, two more quickly. The energy required to move the fourth electron is significantly larger than the third. Just take a look at the periodic table. If you need to pause here, go ahead and do that. But in doing so, you end up removing a core electron. So fourth ionization energy is removal of a core electron. Therefore, we're going to have a huge jump. And again, aluminum is +3. That's why, because we're not going to lose that fourth electron. Way too much energy. And D goes back to electron affinity. It says the energy change associated with gaining an electron is positive for some things and negative for others. This has to do with the fact that some atoms need help. I'll put in parentheses. Some atoms require energy. To accept an electron, i.e. francium. Therefore, those are going to be positive electron affinity values. Okay, and then some atoms actually give off energy when they acquire an electron. I.e. acquire, A-Q-U-I-R-E, i.e. Fluorine. And therefore, those are going to have negative values for their electron affinity. And that's it in a nutshell. So please read your textbook, come and see me if you have any additional questions.